Okay, so now we're going to talk about nuclear energy in a different way. Well, first we're going to talk about how we can manipulate things, all right? First of all, if you're at home, we did this sheet. It was really cool and you missed it. All right, fission. One thing we can do, we can split atoms, okay, on purpose. And we can split atoms to create a lot of heat, okay? We get a lot of energy from splitting atoms, all right? And this is really related to Einstein's E equals mc squared. And basically, the amount of mass that we can convert to energy times the speed of light squared is equal to the number of energy, how much energy we can get out of it. So it's a huge amount, all right? So fission means to split an atom. Here's an example of uranium-235 splitting. We shoot what's called a nuclear bullet. We shoot a particle into uranium-235. Now notice, uranium on the periodic table up there, if you look down the very bottom left-hand corner at uranium, the most stable, commonly occurring uranium is uranium-238, right? So if we go back over and we look on our sheet, you can see it's 235. So we get a pure amounts of unstable uranium, and then we can split it more easily. When we split it, it comes apart. Now, this is called the domino effect, because when we split the first atom, it basically, we'll say, explodes, and that is enough energy to split the atom beside of it. So it goes on and on and on. It's called a chain reaction, or the domino effect. And we first controlled the chain reaction of splitting uranium on the Manhattan Project during World War II under the end zone of a football field in Chicago. True story. I'm trying to remember who it was that did it. Was it Fermi? Yeah. Anyway, so we can control this reaction, all right? Now, fusion means we smash two small atoms together and make a bigger atom. And it occurs in the sun, it occurs in stars. And here is a tritium, or hydrogen, that weighs 3, and deuterium, hydrogen with a weight of 2. We smash them together and we get helium, which weighs 4, and then an extra neutron. All right, smashing them together to make a bigger atom creates a lot of energy. So we have fission and fusion. Fission is to split apart, fusion is to smash together. That's all I'm going to say about nuclear energy and fission and fusion. I really don't have much. The nuclear bombs that we make that blow things up big time, the ones that we dropped on Hiroshima and Nagasaki, those bombs operated through nuclear fission, okay? All right. Now, here's our next part of the lesson today, half-lives. The half-life of a radioactive isotope is the amount it takes half of it to disappear. The amount it takes half of it to disappear. So as these atoms fall apart, we measure the amount of how many of each isotope we have. And when our original isotope is cut down to 50%, then that amount of time is called a half-life. You've probably heard the expression half-life before. Now, working in half-lives is like working with exponents, okay? It changes your amounts exponentially, okay? Because a half of a half of a half is an eighth. Does that make sense? All right, I'll show you a formula that'll make more mathematical sense to you here in a second. Now, you see this guy right here? The bones of this guy are Kennewick Man, and if we have time in class, we're going to see a little video on Kennewick Man. If you're at home, you can YouTube Kennewick Man, Kennewick. It's a very interesting story about some bones that were found in the Pacific Northwest, and a crazy court battle and some twists and turns. It's like a whole Dateline episode. And long story short, some bones were found at the edge of a river in the Pacific Northwest, and someone called someone from the coroner's office to come get the bones, and the coroner realized, hey, this isn't a modern human. This person didn't just die in the last 100 years. This isn't a minor 49er that died in the 1800s up here. It's someone much, much older, okay? So then the university got their hands on the bones, and then there was a whole big argument of, hey, where did this person come from? Did they walk across the land bridge from Asia? Were they Native American? Who were they? And we dated how old these fossils were by using carbon-14 dating. Now, if you'll remember, carbon-14 beta-negative decays into nitrogen. And the half-life, ready, here's your word, the half-life of carbon-14 is 5,730 years. And that's written up here. It's just about 6,000 years for half of your samples of carbon to disappear, okay? Now, here is a simple half-life problem. And before we do that, let me draw you like a really, really basic, over-basic idea of how half-lives work. And carbon-14 is a really easy one to use, okay? Now, this is you. Okay, now I didn't draw you as a stick person because I needed you to have some lungs in here, all right? Now, when mammals breathe, the process right here of respiration incidentally creates carbon-14. And that carbon-14 ends up being stored in your bones, okay? Now, your bones naturally have carbon in them, right? You're a carbon-based life form, okay? And if we calculated by mass in your bones, about 50% of the carbon found in your bones is carbon-12. And the other 50% is carbon-14. And this is true for all breathing, respirating mammals, okay? So, if you found a dead body in the woods, and they died recently, and you took a sample, if you carbon-14 dated their bones, and you took a sample, you would expect for them to have 50% carbon-12 and 50% carbon-14, right? Now, the half-life of carbon-14 is 5,730 years. So watch what happens up here, ready? If 5,730 years went by, then half of the carbon-14 would have disappeared. So that person would have 75% carbon-12 and only 25% carbon-14. Does that make sense? Because after 5,730 years, half of the carbon-14 that they originally had disappeared. Does that make sense? So you can see half-life questions worded by percentages, right? Like, for example, a sample of bone contains only 25% carbon-14 when we would have expected it to contain 50% carbon-14. How old was that bone? The answer, 5,730 years. It had undergone one half-life. Another way to calculate half-lives would be to say we started out with 200 grams or 200 micrograms of carbon-14, and now there's only 100 micrograms of carbon-14. How old is this sample? Well, it's divided in half. It's 5,730 years old. Does that make sense? Okay. Now, you're going to be doing some math with this, so stick with it. So here is a pretty straightforward problem. The half-life of phosphorus-32 is 14.3 days. How many milligrams of a 20 milligram sample will be left after 85.8 days? Now, there's many ways to do this, okay? Many ways to do this. It just takes a little mathematical sense. There is a formula that I will show you, but most of the problems are more easily worked just by thinking about them rather than trying to hammer them into a formula. Ready? The half-life of phosphorus-32 is 14.3 days. All right? Now, if 85.8 days goes by, how many half-lives have gone by? So you would say 85.8 divided by 14.3. So do the math on that for me. How many half-lives, how many times has 14.3 days happened if 85.8 days goes by? 6, that's correct. So this sample would have undergone 6 half-lives. All right? So check this out. This is where the growth, or actually the decrease in the sample is exponential. Okay? How much did we start out with? We started out with 20 milligrams, right? I know I was saying micrograms a second ago, but that was a different sample. All right, 20 milligrams. It's going to undergo 6 half-lives. Ready? So we're going to do this. Divide it by 2, 2, 2, 2, 2, 1, 2, 3, 4, 5, 6. Boom. See what you got. So you can literally just take your calculator and say, I'm going to divide 20 in half 6 times. 20, right? Divided by 2, 2, 3, 4, 5, 6. We would have 0.3125 milligrams left. Does that make sense? If we graph this, okay, if we graph this, the graph would look like this. And this is kind of an important thing for you to understand. The graph would look like, we'd go from 20 down to 0.3. It would look like this. It would have a curve, a nice even curve as time went by. Does that make sense to you? It's decreasing exponentially. And I don't know if you learned that in Algebra 2 or what Math 3 or what it is, but this curve, this exponentially negative curve, should make sense to you, that exponential decrease. Now, there's a formula for that. If you're at home and you're like, my mind is blown, or I'm scared to try, what is this thing called math? It's okay. Here is a formula you can use. And now somebody's at home is like, oh, God, that looks worse than just trying to think about it. That's okay. Here we go. Here is the formula. Ready? It's much simpler than it looks. If you're sitting in the room with me, you should write this down. The sample that you will have left at the end is equal to how much you started out with times 1/2 to the T over H. What? What? I'm going to let you write it down, and then I'll explain it to you. All right. Here we go. Let's do this with the last problem we just had, right? The final amount we're going to have left is going to be equal to what we started out with, right? The original amount, which was 20 milligrams. So we're going to say 20 milligrams times 0.5, because that's easier to type into your calculator, to the, and this is an exponent, and watch this. It was 85.8, that was the total time, over 14.3. Okay? People at home, I'm going to zoom in as much as I can so you can see that. All right. Okay. Now let's make this a little bit simpler before we type it into our calculator. Okay? Because typing to this might be hard for you to do. So here's what I would do. Do you remember that 85.8 divided by 14.3, what was that? That was 6. So boom, 20 times 0.5 to the 6th power. How are you going to calculate that? You're going to punch in your calculator. You're going to hit 20. I'm literally going to show you what to type in right here. You're going to type in 20 times 0.5, and then you're going to hit the button that looks like this. Y to the X. And then you're going to hit 6, because the 6 is that X. Does that make sense? In most calculators, that's the way you would type that in. And you'll see that very quickly that it says 0.3125, doesn't it? Right? Okay, because I practiced it here first. So we can try a couple of these for fun, because I know how much fun you think nuclear math is. Yeah, we're going to have a worksheet on it. And I'm going to try to do a sample from it real quick. All right? All right, here we go. See if I can put one up on the screen for you. How about, let's start up here at the top. An isotope of cesium, Cesium-137, has a half-life of 30 years. Okay? If a 1 gram of cesium-137 disintegrates over a period, I wish I would have said decays, over a period of 90 years, how many grams of cesium would remain? There's 2 ways to solve this. One, look. Every 30 years, half of it disappears. 90 years goes by. How many half-lives will have you gone through? 3. So you could just say 1 divided by 2, divided by 2, divided by 2. Just divide it by 2 3 times. If we're going to use our formula, we would very simply say this. Our final amount is equal to what we started out with, 1 gram, times 0.5 to the 90 over 30. Does that make sense? To the total amount of time gone by divided by the half-life. In other words, what's 90 over 30, everybody? 3. So 1 times 0.5 to the 3rd. Does that make sense? So what's 1 divided by 2 divided by 2 divided by 2? 0. What? 0.125. So the easiest way to do this would just be say, okay, 1 divided by 2 divided by 2 divided by 2. 0.125. And that makes sense. So that'll be 0.5, 0.25, 0.125. Does that make sense? Some of the problems are that easy. People at home, good luck. I'm going to try to give you a simple worksheet and stuff.